Hi, this is Mrs. Murdock, and I'm going to review, remove water potential and the tonicities. So this is a review of, remember that 3-beaker lecture that we did a while back? And we talked about the situations in each beaker and the consequences to the cells and the consequences of water movement in each of the beakers, right? My beakers. And each beaker has a solution in it of water. And then floating in that solution is a giant red blood cell, nice and big so we can see exactly what might be inside the red blood cell. So I'm just going to write the terms underneath. Hypertonic is going to be describing the solution outside the cell in this beaker. Isotonic is the middle one. And the last one is hypo with an O, tonic. Bring that up a little bit. Whoop. Just move myself. There we go. Hypotonic. Hypotonic describes this solution out here. Okay, so remember that in each one of these beakers, there's not just one solution, there's two. There's the solution outside here that the cell is floating in, and then there's the solution inside the cell, which is the cytosol of the cell. Remember, if you have blood plasma is just water with stuff dissolved in it. And then inside the red blood cells, the cytosol is also just water with stuff dissolved in it, right? So two solutions, let's take them one at a time. Hypertonic means more solutes out here than the one in here. Anytime you use any one of these tonic terms, it's a comparison term. Bless you. It's a comparison term that means nothing unless you're comparing it to something else. So if it's hypertonic out here, it also follows this hypotonic in here, by the way. So let's say that out here is 0.8 molar salt. And in here is 0.3 molar. Hence, it's more solutes out here than in here. There we go. Now, what's are going to be the consequences to the cell? Which way will the water flow to help equalize the concentrations on either side of the membrane? The water will flow out. Very good, because water will always flow towards where there's more solutes to dilute it out here and to equalize concentrations on either side. That's what the natural laws of diffusion are always going to try to do. And it's always water that's going to tend to move the fastest and the first, because there's more aquaporin channels in living membranes than any other kind of channel. So what's going to happen to this cell as a consequence? It's going to shrink. Of course it will. Just like you kind of shrivel up when you go in the ocean, right? You go in the ocean, it's really salty. The ocean is hypertonic to us, so all of our little thin membrane parts of our mouths and eyes, we tend to lose water from those places, and we feel a little bit shriveled up when we come out of the ocean. Same thing. This is not a happy solution for any living cell. Animal cells don't like it. Plant cells don't like it either. It's not a good situation to be in a hypertonic solution. Okay, isotonic means same. So that's going to mean, like, for example, if it's 0.3 in here, it's 0.3 out here. The consequences of water movement is that there's a net movement of 0, but there still will be a dynamic equilibrium going on that's often drawn like that, right? So the cell likes that. Animal cells ideally like to be in an isotonic solution. So your blood plasma is almost the exact same concentration as the inside of your red blood cell cytosol. That's a good thing. Okay, hypotonic means that maybe we'd have 0.1 molar salt out here and have still the 0.3 in here. Less solutes out here than in here. And that reverses the water flow so that you get water brought into cells. As a result, cells will swell, and in some cases, especially with animal cells, you could have cells bursting, which is not good not good for animal cells, but plants actually like this. Plants like it. In fact, plants are designed for it because plants have something that animal cells don't have. What do they have? Cell walls. So actually plants, if you pour pure water on them, they do fine with that because they absorb it, and then their cell walls are designed to offer a rigid boundary so that when the vacuole swells up, that's like their skeleton, right? They don't have a bony skeleton the way an animal does. Instead, they have millions of cell walls that if you pressurize them, the whole plant stands up and reaches the sunlight. That's the adaptation. Okay, so now if we go down, let's talk a little bit about water potential then. What exactly water potential is and how it fits into this. Because water potential does fit into this. You can explain water movement in terms of reaching equilibrium, in terms of tonicities, right? Where water will always move towards where there's more solute molecules to dilute them, to equalize concentrations. You can talk about it that way. Or you can talk about it in terms of water potential, which is a measure of the energy, or the free energy of water molecules, of particularly the water molecules in a solution. And it's a pressure. It's a measure of pressure in a unit called bars. Right? So here's what happens if you have the effect is this, that if you have a solution of water, just a solution of water, and it's got some salt in it, right? Maybe it's 0.3 molar salt. And then you have another solution next to it that has 0.9 molar salt. Which one do you think, which beaker has the water molecules that have more energy? This one. So what happens here is this, that the more solutes there are in the water, the more they bind up the water molecules. That's what happens, right? Okay, so water potential, remember Mr. Anderson with the pitchfork, right? Water potential decreases with more solutes, right? So the more solutes you add, the less the water potential is. But it increases it increases as you add pressure. As you add pressure to the system. So then you have the two equations. That is total water potential is equal to the pressure potential, whatever it is, plus the solute potential, whatever it is. And in the experiment that we did with the potato slices, because we were at sea level and because we had open beakers, they told you, oh, the pressure potential is 0. So in our experiment at sea level and 1 atmosphere pressure and an open beaker, there is no pressure to speak of, so you don't worry about it. But the solute potential is calculated according to how much solute there is, and with some other with this equation. Remember this? negative ICRT. So remember that, and that becomes your total if the pressure potential is 0. And if you recall that, again, remember you're going to be able to use your formula sheets on the AP exam. So there's a couple things you need to know. -1 you just keep out there. I is the ionization constant. So if we're using sucrose, because sucrose doesn't dissociate into anything, it just stays in one molecule in water, then it's 1, right? And since with our potato experiment it was 1, I'll just keep it with that. If it's sodium chloride, though, your I value is going to be 2, because when you put sodium chloride in water, it dissociates into 2 ions, right? So just watch to make sure whatever solute they're using, it's going to change your calculation. The C value is the molarity of the sucrose inside your potato in terms of our experiment. So we got that. We got that by graphing the data. So there was a 0 line, remember? And then if you're above the line, the potato gained mass, and below the line, it lost mass. So this was the delta change in mass. And then down here were the concentrations of sucrose that it was soaking in. Remember, we soaked them overnight. And then the line looked like that, right? And where it hit the 0 line, that's called the isotonic point. The isotonic point is important because that tells you that that was the point where the potato didn't gain or lose any mass. So whatever concentration that interpolates to must be the same concentration as the inside of the potato, because they're the same and the water didn't move. So then in this case, from this graph, your C value would be 0.4 from interpolating from the graph data. That's not your water potential, that's your sucrose molarity, right? R is just a constant. You get it right off your formula sheet. It's 0.831. It will always be that, so you just do that. And T is temperature in degrees Kelvin. So for example, if it's 21 degrees Celsius in the room, you would add 273 to that to convert it, and then you would plug and chug to get your final water potential. So just really fast review of water potential and how you can calculate it, right? They might also give you the kind of problem where they'll say, if you go back up here, and for example, what if they said, well, actually there is a pressure potential. The pressure potential is +5, let's say, okay? And then your solid potential, they'll give it to you, maybe that is -9. And if they give you these two values, what would your total potential be? -4, right? This +5 and -9 together would be -4. They might give you that kind of problem too, it just depends. Okay, so that's a little review of water potential and a little fast review of the actual lab that we used to calculate the water potential of potatoes. And I hope that's helpful.